Hi, I'm Jason from Postech, and today I'm going to present this paper, Bounded Model Checking of PLC ST programs using rewriting Modulo SMT. The outline of this presentation. First, I'm going to briefly introduce what PLC is, and then the existing model checking approaches of PLC, and then our contribution, and finally, I will present a case study and experiment. PLC stands for Programmable Logic Controller, and it's an installable computers that logically control systems in the industrial sites. So instead of designing and making circuits for each and every purpose, one can just use the same hardware device and write different programs so that it's very flexible and it's easy to maintain. So it has been widely used in the industry, such as airplanes, ships, or conveyor belts in plants. And in all these sites, errors can cause a catastrophic damage. So there's no need to mention that PLC systems are safety critical. There are several languages we can write PLC programs, and some of them are graphical, such as ladder diagram or function block diagram, and some of them are textual, such as structured text, in short ST, and this language is our focus today. ST supports assignments, loops, and conditional statements and function calls, and so on. It just looks like a typical imperative programming language with function calls. So about the existing techniques, since 90s, model checking of PLC programs have been studied for all these languages. And these approaches, conventional model checkers are used, such as new SMV or CBMC. And it was effective. For example, CERN has developed a tool called PLC Verif, and including this work, these model checking approaches translate the PLC programs to input model that is acceptable to model checkers. And when we translate something, it's always hard to guarantee that one is the same as the one after the translation. And also, these works tend to focus on specific subset of language or specific properties. There were alternative approach, which was to formally define PLC languages itself. Such approach includes works using K framework. K is a rewrite-based framework for defining language semantics, and it has successfully implemented the semantics of big languages such as C, Java, and JavaScript. And K semantics of C passed over 99% of GCC torture test suite. The strength of K is that the K semantics is, when it is defined, is automatically executable and modular. It means if we want to add a language feature, we can just add the new added part and not update the existing part. A language semantics is defined by specifying K rules, which looks like this. I brought here two of the most typical K rules for imperative programming language: lookup and assignment. For each K rule, there might be one or more horizontal lines like this. And those K rules describe state change from above the line to below the line. And when there's no line, it means there's no change for those parts. So the lookup, when we look at this rule, variable X is replaced by V by referring to environment and store. the assignment rule, the assign x equals 3, the statement is consumed, and then the store location, the appropriate store location, the value is updated to v. So that is how we define language semantics by using K framework. There has been work using K framework that defines PLC languages, and for those approaches, there's also some limitations. In a sentence, it was hard to capture the PLC systems as a whole. First off, it focused on single execution of programs, and also it focused on internal program verification, and also they do not cover some time-related features, such as timers. So let's look at an example. It's traffic light in an intersection, and this PLC program controls the color of traffic lights for both directions through multiple cycles. The cycle, I'll explain it in more detail later. And these vertical bars represent the start of each cycle. And in each cycle, it takes in the signals indicating the arrival of cars or pedestrians. So this simple example shows that with the existing K work, it is hard to describe PLC systems as a whole. So our approach, our contribution, in short, enables the comprehensive system-level PLC verification. We did that by extending the semantics to cover cyclic and interactive behavior of PLC. And then we developed a method for bounded symbolic LTL model checking. For the second part, to elaborate the second part, let's think about the traffic light example, and we want to verify the property such as car lights cannot be both green at the same time under any arbitrary car and pedestrian arrivals. This problem is a typical bounded model checking problem. And since we are not looking at a fixed situation, we are looking to consider all possible situations. We want it to be symbolic. And then we implemented the above method into a tool called STBMC, and we demonstrated the usefulness of our tool by presenting a case study and experiment. The first part of our contribution, we implemented scan cycle as a whole. When PLC is running, it basically iterates scan cycles. And a scan cycle consists of input, program execution, and output stages. Input takes in the environmental signals and store it into input variables. And then after the execution of program, in the output stage, it reflects the value of output variable to the controller. It realizes the program into the hardware device. For example, let's say there is an input variable called incoming and output variable color. And in the first cycle, let's say it gets the signal, the false Boolean signal, and then the value of incoming is set to false before the program execution. And after the execution, let's say the variable color has the value red. And then in the controller, in the output stage, it reflects the value red and turns the hardware device, the light to really red. And then after that, it repeats the whole process over and over. And to implement this, we have defined input and output streams because it just looks like a stream of values and also in the output. And some IDEs support program scheduling, and this makes implementing scan cycle a little more complicated. This feature, program scheduling, allows programs to execute not every cycle. Let's say there are three programs, P1, P2, P3, and P1 executes in every cycle, and P2 executes in every 2 cycles, and P3 in every 3 cycles. Well, these P2 and P3 have some strides between two execution, and we are going to call this size of strides period. So P1, P2, P3 have a period 1, 2, 3, respectively. And there's also something called phase. Phase means how many cycles it has to wait before it executes again. So the period, the program 2 must, the phase of program 2 must be set to 0 when we want it to be executed in the first cycle. And for program 3, it has to be, the phase has to be 1 so that it starts from the second cycle. To implement this, I brought here 2 of the K rules we used. The first one, SC skip, is skipping the program execution when it is not its turn. We know it is not its turn when the phase is not 0. So m plus 1 becomes m as it skips, as it gets out of the program list. SC exec is the second rule. It executes the program when it is its turn to execute. And when we know it when the phase is 0 and it is set to n minus 1 and n is when n is the period. And here it actually calls the program. The second semantics extension point is time. And time is a very important part of PLC systems. Obviously, because PLC works in real-time environment. In some IDEs, users have control over the length of scan cycles. So users might set the duration of one scan cycle as 500 milliseconds or 600 milliseconds or so. And also there are time-related function blocks, such as timers or pulse generators and so on. Especially there are some functions called wait and wait time. And these functions are related to both time and program scheduling. For example, wait B halts that program execution until B becomes true. So here there are 3 rules to implement wait statements. Upon encountering a wait statement, it first evaluates its argument. And then when it's true, when it is evaluated to true, it just consumes the wait statement and move on. When it is false, then it sets the phase to 0 so that it gets executed in the next cycle. And then the rest of the configuration must be stored somewhere to be brought back intact in the next cycle. So after the semantics extension, we have developed bounded symbolic LTL model checking. Given a PLC program, we want to verify the following properties. I explained it before. Highlights cannot be both screen at the same time under any arrival signal for 8 cycles, let's say 8. And to use the conventional model checking notation, it can be expressed like that. When in a configuration, it includes all the input sequences. And since we want to consider all possible input sequences, explicit state model checking will surely lead to state explosion, especially when we're looking to consider multiple cycles. So to do that, to resolve this issue, we applied rewriting modulo SMT. Rewriting modular SMT is a technique. I am not going to go on detail of rewriting modular SMT, but it's a rewrite-based technique that allows us to symbolically execute and analyze set of states in the system. So how did it do this? Rewriting modular SMT only supports existential reachability problem, and that's the template of the existential reachability problem. And here, T and T prime are term patterns, and the command here symbolically searches for states that are reachable from T, match the pattern T prime, and satisfy the condition psi. So this is the problem we wanted to solve, the model checking, LTL model checking problem. And that's the problem that our tool supports. So what we're going to do here is to reduce this problem into that existential reachability. And this left-hand side, program state and initial configuration can go into T, encoded in T, and the search bound N can be encoded somewhere in T prime, and the LTL property we want to verify is of course negated and goes to psi, so that the search command looks for the counterexample of this LTL property. And we were able to automatically translate this from that. So our tool, let me talk about our tool STBMC. It just implemented the method we developed, and the user needs to only give two things, the PLC program and the requirements. And everything else, the semantics, we provide the semantics, and the model can be automatically compiled, and the requirement is also automatically compiled into the proper search command I just explained. And everything else is automated, and users can get the result, analysis result, which is success message or a counterexample. So let's look at the traffic light example in more detail. It's an intersection of north-south NS and east-west EW directions, and well, there are 6 system inputs: car incoming signals and pedestrian incoming signals. And also, let's say there's non-deterministic network delay that affects yellow time. And here, once again, the vertical line represents the start of each cycle. And when these signals, Boolean signals, encode the arrival of car in specific moments. So the property we want to verify is, first, both car lights cannot be green at the same time. And second, a green light cannot turn red without turning yellow first. And to make it more interesting, let's say the car lights have some mode switch. The car lights, basically, it follows some schedule. It circulates the color red, green, and yellow. And one round of colors takes 7 cycles, let's say. But when there's no car coming for a while in a certain direction, it does not have to go green. It stays red, just like this, so that the other light can stay green. That way, we can make it more efficient. So for the property 1, this is the actual requirement file user needs to provide. There are 6 system inputs, and these 2 question marks denote the symbolic input, which is completely unknown sequence of input. And step size, the step bound is given as 8, which means, and the round of color was 7 cycles, so 8. the bound of 8 is pretty reasonable. And the condition is given as this: globally not NS green and EW green. And this is the success message. And for the second property, all the other settings are similar, only the condition differs. If it is green, in the next cycle, it must not be red. And this time it returned a counterexample. And these three rows is the input sequence that leads to a counterexample. And the bottom two rows are the output sequence from the above input sequence. And when we have this, without this, it is really hard to debug. We all know that debugging is difficult. Auto localizing is also difficult. And when we have this specific input sequence that leads to a counterexample, it is very useful when it comes to debugging. And we were able to fix the bug, and after that, it returned the success message. So for the experiment, the question was, how fast is our tool compared to previous approaches? And well, the PLC Verif was the tool of our choice to compare against. And we used 14 benchmark models that whose size varies from 32 lines to over 2,000. And this is the table. The PLC Verif N is PLC Verif with new XMV, and PLC Verif C is PLC Verif with CBMC. And there are a lot of number. What I'm trying to say here is that STBMC showed comparable performance against PLC Verif. And as far as I know, PLC Verif implemented a lot of optimization techniques such as program slicing. STBMC, we did not implement anything yet. So after we apply those optimization techniques, we expect our tool to perform much better. So the conclusion: the translation-based PLC verification focus on specific domains, and the alternative approach K-works was effective but lacking some key features like time-related features and scan cycles and so on. And our approach is very comprehensive. We were able to symbolically model check up to bound, and we implemented our tool, and we demonstrated the usefulness of our approach by presenting a case study and experiment. Thank you.
Okay, great. So we have some time for questions. Any questions? Oh, yeah.
Hi, interesting talk. So I have a little question regarding the K work.
Yeah.
So is that K does not directly support time feature? I think that's true. But do you have to try that to implement your own rewriting rules towards those time functions?
Rewriting rules?
Yeah. So in terms of K, that you actually can define your own rewriting rules. So for example, weight, you might have internal log, then you can implement the internal log. In terms of like evaluation, is that we execute this time function, you can write how this time function is actually executed.
I'm not sure if I follow the question right. We said we extended the existing semantics, and that is by adding K rules to include time.
Yes, you can. I think you're able to implement your own syntax.
Yes.
Towards the way the time function. So I'm just asking that if you have tried this approach, or did you fail or find any problem with it?
Well, I think we are talking about the same thing.
Okay.
Yeah, let's talk later.
We can talk about that.
comments after wake up. You want to go into the evaluation slide again for a second? I noticed that there were, when it came to the stack example, that's the one case where it seems like the numbers are a lot higher. I guess I was curious what stack was. Do you have any idea why it's taking a lot longer in that case?
So I believe you are referring to this case.
Yes.
And we suspect that this program is the property and this program are not really related. I mean, it's the property checks the unnecessary part of the program, and the program slicing, it cuts out the unnecessary part of the program, and which PLC Variable did implement, and we didn't. So that's what we're suspecting.
Okay, that makes sense. Like program slicing is separately, but this is optimized. So yeah, that makes sense. Great, thanks.
Cool. Any other questions? So I actually did have a question. So I was a little bit confused in the implementation of your tool. So if you show us the slide, yeah. So you're not using K at all here, or you are using K in the tool itself?
We are using the K technique, but like K framework came with a K tool.
Yeah.
We did not use it.
Okay.
But we used the methodology.
K uses Mod, right? Mod.
Yeah, as far as you know.
So it's quite what you've developed is similar to K in some ways because it does also perform rewriting, but has some additional features for time. Is that the key difference, or?
Well, K tool supports explicit state model checking, and we want to symbolically do it.
So the SMT solver is providing the symbolic.
Yeah.
Okay. Thank you. Cool. Just have a look if there are any questions online. Well, I can't see any questions online at the moment. Any other questions? One more question.
Hi, great talk. I heard you mentioned that there was one situation where you did the model checking and gave a counterexample and you fixed the bug in your code. So I was just wondering, did that happen, was that the only bug, or were there multiple iterations of finding bugs and then fixing them using your tool?
I'd say the only interesting bug that actually helped us fixing the bug. Yeah. Thanks.
Thank you.
Great. Okay, thank you.